Let's look at some of the big ideas related to the least square regression line. So we know that our model is the predicted y is equal to a plus bx. It's just linear, where a is your y-intercept and b is your slope, and you are now an expert at interpreting these values. We've learned that the model minimizes the sum of the squares of the residuals. The sum of the residuals is always 0, and so would the mean of the residuals. We've also now seen that the point that will always fall on the least square residual line is the point x bar, y bar, so the mean of the x's and the mean of the y's. I would encourage you to pull out your formula sheet. This formula for slope, which is b in our line, is given on your formula sheet. It says b is equal to r, which we know is our correlation coefficient, times the standard deviation of the y's divided by the standard deviation of the x's. No need to memorize that. It's given to you. Just pause and find it so you know where it's at. Now, you are also indirectly given a way to calculate your y-intercept, and it's derived from another formula given to you on the formula sheet. Since this is a point on your line, you could plug these values in for x and y, and that's the formula given. You're told that y bar is equal to a plus b x bar. So all they've done is they've plugged in that mean point. You could solve for a by simply doing a little algebra, subtract b x bar from each side, and now you have it solved for the y-intercept. So indirectly, off of your formula sheet, you can get that a is equal to the mean of the y's minus your slope times the mean of the x's. Last thing I want to talk about is about the name. What's in a name? So it's least square regression line. Line, well, we've got that. We know it's always a line. Least squares, you saw that in the College Board video, that you are reducing the sum of the squares of the residuals as much as possible. So least squares, it's all about minimizing those residual squares. So what is this R, the regression, all about? To best understand where that word is coming from, to regress is like to fall behind. It really comes from understanding your slope. So your slope is defined as correlation coefficient times the standard deviation of the y's divided by your standard deviation in your x's. Again, just think good old slope, change in y over change in x to help you remember this part, although technically it's, again, on your formula sheet. All right, so if I think about this and make this a fraction, my bottom number is 1. So when we interpret slope, I could say that for every 1 unit increase in the standard deviation of the x's, the y is increasing by r standard deviations in y. For every 1 standard deviation in x, I increase r standard deviation in y. So looking at the number line, think of it like this. If I go up 1 standard deviation in x, how much is it going up in r? Well, or going up in standard deviations of y? Well, r, remember, is a value between -1 and +1. Very rarely is it ever equal to 1. It's usually much smaller unless it's exactly a linear relationship. A high correlation, is 0.8, 0.9, very high. But it's, again, smaller than 1. So therefore, as I go up 1 unit in standard deviation in x's, I'm going up r standard deviation of y. It's falling a little bit behind because r is going to be less than 1. So I've kind of stated that over here. For every 1 standard deviation in x, we go up r standard deviations in y. So y is always regressing or falling behind x. So that should help you see where all parts of the name least square regression line comes from. Now let's look at how to use summary statistics to calculate the least square regression line. So again, summary statistics are like your mean, your standard deviation, and you can find your least square regression line using the big ideas we just discussed. So in this example, we're told there's a moderately strong positive linear association between the height of adult males in inches and their weights in pounds. And below is a list of the relevant summary statistics. We are told to find the slope of the linear regression line. So in general, our model is y hat equals a plus bx, and if I'm looking for the slope, that means I'm trying to find b. Since I'm not given the raw data, I think about my summary statistics, I look at my formula sheet, and it reminds me, oh yeah, b is equal to the correlation times the standard deviation in y divided by the standard deviation in x. So here's my explanatory and my response variable. Here is my correlation coefficient, or r. So it's a matter of simply substituting. This gives me b is equal to 0.768 times 21.05 divided by 2.18. Put that in my calculator, and I get that b is approximately 7.416. Take it out to the thousands place. Now I'm going to interpret. So I'm stating that for each additional 1 inch increase in my explanatory in height, the predicted weight increases by 7.416 pounds. Make sure, as always, that you're saying predicted weight, not just weight. Now we need to write the equation of the linear model, and we're going to use our model then to predict the height of a male. So I need to find my y-intercept, which I know is equal to, from my formula sheet, I can derive it's the mean of the y's minus b times the mean of the x's. So I'm going to substitute. The mean of my y values would be the average weight of the males would be 153.6 pounds, minus my slope, which was 0.768 times 21.05 divided by 2.18. Now I know I just got this value, but just out of habit, I often will type it all into my calculator because every time I round, my answer gets a little bit wrong. So I already had a rounded answer right here, and I don't want to round twice. And it's not hard to type this in the calculator. The mean of my x's is 71. All right, so pause, pick up your calculator, crank that out. I get an a value of negative 372.920. And this very well may be a case where it doesn't always make sense to interpret the a value in context, because here you would say that the height of a male with the height of a man who is 0 inches tall weighs negative 373 pounds. That really makes no sense in context here. So sometimes your y-intercept is kind of nonsensical. All right, let's write our linear model. So my predicted weight is equal to negative 372.920 plus 7.416 times the height. I am then told to use it to predict the weight of a male who is 75 inches tall. So I'm just going to substitute. So I plug in, crank that out in my calculator, and I get that he is approximately 183.28 pounds, or he's predicted to be 183.28 pounds. Third thing I'm asked about this set of data is, what proportion of variability is explained by the regression model with height? Okay, so this goes back to our last lesson. The proportion of variability is your r squared. So we were given r, so you do what you think. You would need to square it. So we're going to square 0.768, and that is approximately, 0.590. Take a second and see if you can interpret this. This is stating that about 59% of the variation in your y, so of the variation in men's weights, can be explained by this model, by the least square regression line with their heights. So here's my statement. So only 59% of the variation in men's heights can be explained by the least square regression line with height. So the other 41% is attributed to other factors. It might be diet, could be, just genetics, all sorts of things, but it's not explained by the model. What would you predict about the weight of an adult male who is 2 standard deviations above average in height? To answer this, we need to think about what we know about slope. So slope is defined as r times the standard deviation of, in this case, it would be weights divided by the standard deviation in your heights. Change in y over change in x. Okay, so this means that for every change of 1 standard deviation in height, we are going up r standard deviations in weight. So the idea here again is for every 1 standard deviation in height, we change r standard deviations in y. So this problem is saying if we go 2 standard deviations above average in height, well, that means if we're multiplying, in other words, the bottom by 2, we're multiplying the top by 2. We would change, my answer would be 2 times r standard deviations in my weight. So if I just, to answer this, I would take 2 times my r value, which is 0.768, which is approximately, means we would be approximately 1.536 standard deviations above average in weight. 5 is asking something similar. If a male is 1 standard deviation below average in height, what would you predict about his weight? So similarly, if he is 1 below in height, his weight is going to change by r standard deviations. So it would be 1 times r below, because it would have direction as well. So r is 0.768 again, so it would be about 0.768 standard deviations below average in weight.